Welcome to Microlecture 12, where we are using pKa values to predict the direction of an acid-base equilibrium. This time I'm going to give you a different looking pKa table. You should be able to read any table of pKa values that is given as a reference. Okay, so I'm going to give you some acid-base reactions that will probably look pretty familiar, like water reacting with HCl and an acid-base equilibrium to give rise to hydronium and chloride. Alright, so just to be thorough, I guess, with all of my electrons. So there you have an acid-base equilibrium reaction. I'd like you to look up the pKa values of the acid and the conjugate acid. Pause the video and do that, and then come back. Okay, so HCl, if we look that up, has a pKa of -7, and the hydronium has a pKa of -1.7. So the one with the lower pKa is the stronger acid. Remember that equilibria favor the direction of strong to weak. And so this is the stronger acid. This equilibrium is going to favor the forward direction. And so this is the situation from general chemistry when we said K is greater than 1, because the concentration of the products is going to be greater than the concentration of the reactants if the reaction favors the forward direction. And so you see, we can predict the direction of any acid-base equilibrium reaction based off of pKa values. So let's do another example. This time I'm going to pick acetic acid and ammonia. So likewise, just look up the pKa values. You'll see the pKa value of acetic acid on this table is 4.8, and the pKa of the ammonium ion, the conjugate acid, on the product side is 9.4. So we can clearly see acetic acid is the stronger acid, and reactions prefer stronger to weaker, so K is going to be greater than 1 again. So each of these reactions favors the products. Let's see about another one. So we've got a negative charge on a triply bonded carbon atom there, and we're reacting this compound, a 6-membered ring. It has many hydrogen atoms on it that can serve as protons, which just draw in one of them. And this equilibrium reaction would give rise to this alkyne product, and a 6-member ring with a negative charge on one of its carbons. Okay, so go ahead and look up pKa values of these species, or species that are as similar as possible in the pKa table. Okay, so what I found was an alkyne. It's not the same alkyne, but we know that from this table that the pKa of the alkyne on the product side is going to be about 26. And what else do we know from this table as far as hydrocarbons? Well, we've got just CH4 to go off of because nothing else really just looks like a hydrocarbon that doesn't have other, functional groups attached to it or double bonds or anything like that. So this is going to have a pKa of 49. Okay, and so we know that our stronger acid is the alkyne, and the reaction is going to favor the direction going towards the reactants. Okay, so I would not expect the product concentration to exceed that of the reactants, so K is going to be less than 1. So make sure that you can use a pKa table like this to predict the direction of reactivity for any acid-base equilibrium, and keep up with the curved arrow notation and making sure that you can push electrons to write out the mechanism for all of these reactions.